Hey everyone, today we're going to be talking about how to use limits to determine how functions grow relative to each other. Let's begin. So logically speaking, whenever we're thinking about two functions growing in relation to each other, either one function grows faster than the other, or that function grows slower than the other. So the way that we actually end up testing this is like this. So if we have two functions, f of x and g of x, well then if f of x grows faster than g of x, then the limit as x approaches infinity of f of x divided by g of x will equal infinity. Let's think about why that makes sense. If f of x is a function that's going to get really big, really fast, and way faster than g of x, then g of x is going to be no match, essentially, for the speed of f of x. And so f of x is going to get so big, way quicker than g of x, that the limit will just approach infinity, because f of x is just that big. We can also have the case that g of x grows faster than f of x. So then if that's the case, well then the limit as x approaches infinity of f of x divided by g of x will equal 0. And it's kind of that same principle. If g of x is going to grow way faster than f of x, then g of x is going to get huge compared to f of x. And if you divide by a huge number, you essentially just end up with your 0. So let's try this relative growth problem with polynomials in the fraction. So here we see the top function is x cubed minus 2x squared, and the bottom function is x squared plus 1. So really there are two ways to go about doing this. There's a mathematically formal way, and there's kind of a cheating way that I will show you. But just for the sake of you seeing the rigorousness in the math, I'll show you the formal way first. So what it involves doing is we have to divide by the term with the highest degree. And as you can see here, x cubed is the term with the highest degree, so let's divide everything by x cubed. When we do that, we end up with this. So to kind of simplify things a little bit, we can write this as 1 minus 2 divided by x divided by 1 over x plus 1 over x cubed. So now is when we plug in the infinity into everywhere we see an x. So this one here is safe, it doesn't have any x's by it. But here, this 2 divided by infinity, well, 2 divided by infinity is just going to be 0. That's going to go to 0. Infinity is huge, so that'll go to 0. Same thing over here. 1 divided by infinity will go to 0, and 1 divided by infinity cubed, that's going to go to 0 even faster. So essentially, we end up with this situation where we have 1 divided by 0, but this 0 here is actually a 0 plus, because these numbers never really approach 0. They just approach numbers that are really, really close to 0. And so it ends up being a 0 plus. And we've seen from before that this just ends up being positive infinity. So this limit actually is just positive infinity. So that's telling us that the function on top grows faster than the function on the bottom. Now let me show you the cheating way to do it. As you saw from here, everything that wasn't the highest degree on the numerator and wasn't the highest degree on the denominator kind of just went away. So we can do that and kind of skip this step and just go straight onto something like this. We can ignore the negative 2x squared and the plus 1 and just go straight to focusing on the term with the highest degree. So here, that's just super simple. These divide to form x, and if you plug in infinity into x, well, you get infinity. Pretty simple. So as you'll see, these questions are really simple whenever you just use that cheating way that we just went over. So now we're going to try to take the limit as x approaches negative infinity of x squared plus 1 divided by x cubed plus 2x squared. So first, something I actually forgot to do in the last one is that we always have to plug in the limit value whenever we have a limit problem. So if we try to plug in the negative infinity here, we get negative infinity squared plus 1 divided by negative infinity cubed plus 2 negative infinity squared. And essentially, well, you can tell this is going to be an infinity over infinity. The sign doesn't really matter. We just see that it's an indeterminate form. So that's why we had to do that algebra from before to figure out what the limit value should be, because it was an indeterminate form. But we know that tricky cheating way from before. So now we just make it into x squared divided by x cubed. And this does become 1 over x. And so that is a 1 divided by negative infinity. So essentially it becomes 0. Okay, let's try out this last example. So if we try our cheating method, we'll do the limit as x approaches negative infinity of negative x cubed divided by the square root of 9x to the 6th. And notice here that I transferred over the square root because we can't just change what is in the limit. So now, to keep track of the sign, because that actually ends up being pretty important, let's just plug in this infinity straight into the function here. So we end up with a negative infinity cubed divided by the square root of 9 times negative infinity to the 6th. So let's kind of reason out what this should end up being. So if we have a negative cubed times a negative, that ends up being a positive. So we end up with a positive infinity to the cubed on the numerator. And on the denominator, we end up with 3 because square root of 9 is 3. And then here the sign is a negative 1 to the 6th power. So that ends up actually being a positive 1. So we just end up with a square root of infinity to the 6th power. But the square root and the 6 just become a cubed. So these two are multiplying. And here, pretty simple, just see that these two infinities cancel. We end up with our final answer of 1 over 3. So that means that the limit is just 1 over 3. And you actually can have numerical values like these that aren't infinity or 0 whenever we have these types of relative growth problems, because actually, if you notice here, the degree on the top is the same as the degree on the bottom. So that's how we end up with that. It's kind of the ratio between their growths. And again, remember, it's really important to keep track of the sign whenever we're doing these problems. Even with this problem right here, if we have a negative infinity, this earlier problem, we would have had to keep track of the sign. So that's really important. Be sure to always keep track of that. That just about wraps everything up. Thank you for watching and have a great day.